Hello, it's Scott Manley here, and today I'm looking at Universe Sandbox 2. We don't have the universe here, we have the solar system. Universe Sandbox, you may have seen on Steam, and in fact you may have probably picked up a copy if you are a regular buyer of Humble Bundle, since it's been in there a couple of times. Universe Sandbox is not a game, it is a physics simulation for modelling the motions of planets. However, I will admit that in the early days of Universe Sandbox, I was very dismissive because its mathematics were actually kind of cheap and rubbish. Thankfully, Universe Sandbox 2 has really, gone out of its way to make sure that people like me are happy. And they provide a bunch of different algorithms for integrating the equations of motion and making everything happen quickly. This whole little menu here covers everything that I might need to know. Actually, it covers a bunch of things. It doesn't cover everything, but I am not your typical consumer of this. I used to write code that did this, but I used some pretty fancy techniques. But this is brilliant compared to what we used to have. I mean, you see on this list we have Euler explicit is utterly terrible and should never be used. But if you go down to Runge-Kutta 4, that's about the best you'll do. And RKF, I presume, is Runge-Kutta-Filberg. And those are getting better. And Velocity Verlet, you get into things like symplectic integrators where you understand that it's a physical system which not only follows certain rules for velocity and momentum and things like that, but also preserves things like energy and momentum. Anyway, you can see here the accuracy. Well, this is something you can tweak. So if I take the step size down here and I bump it up, so we're running, say, at 53 days per second. So we're running a few weeks per second, 5-7 weeks per second. And now if I go into gravity, watch this as I increase the tolerance, right? So by increasing the tolerance, that means that we have to get more and more accurate. So if you're predicting a space probe and you want to hit a tiny window, you probably want a higher tolerance so that you're getting things more accurate. But as I increase the accuracy, we're aiming for 11.7 centimeters accuracy. Look what happens. This time has turned red. That's meaning that the accuracy is slowing the simulation down. If I drag it even further, the frame rate is slowing down and it's actually not able to advance time as quickly as you'd like. Now, this is of course asking for less than 1 millimeter precision, which is rather unrealistic because to get that, it's having to take thousands of steps to get there, and you'll also find that there are errors just simply by adding and subtracting floating point math. So if you actually increase your accuracy or increase your tolerance too far, you will end up getting a less accurate simulation. You just have to understand all these things. Anyway, so we're modeling the motions of things. You can tweak numbers. For example, let's take Jupiter. Oh, there's a Jupiter here. Incidentally, you can see we've got an asteroid belt, but we also have Trojans. So what we could do with Jupiter is, say, edit its eccentricity. That'll be fun. Let's knock that up a bit. Oh yes, let's have Jupiter. Let's just do that. Let's have Jupiter that just goes completely insane. Okay, and let's watch that run. It'll take a while to get there, but it'll probably cause chaos as it falls through the solar system here. Look at it. It's going to fall down like a veritable comet and possibly kick things all over the place. Whoa, look at that. Any asteroids sent off into strange orbits? Maybe, maybe not. We'll find out. The other thing you can do, one other thing you can do, is if I can click on the Earth, there we'll go and zoom in on it. So I can follow it as it flies around the sun. It's a little fast to follow at this speed. Might give you some might trigger some spasms or whatever. Okay, was it position? No, we don't want position lock. We want hide rotation, so we can actually just see what it looks like. There we go, zipping around. Now we have a climate model that's been added, and this isn't the most accurate climate model. I'll tell you right away. Do not base your policy decisions based on what this says. However, it is a great toy to understand that if you increase carbon dioxide, you will get a feedback in the system, and there's multi-layers to the climate. As you increase the temperature, you will get clouds forming. The clouds will increase the albedo, which will decrease the amount of temperature coming in. But you can do these things. You can just bump up the number to like 1,000 parts per million of carbon dioxide, and immediately you see the temperature starts to rise and then go down. A lot of this is due to the temperature oscillation through the year is in part due to the fact that the northern hemisphere has more land and therefore absorbs heat in a different way to the southern hemisphere, which has oceans. But over time, the amount of carbon dioxide in the atmosphere will drive the temperature up over time. You can adjust the amount of materials on the planet as well. If I come in here, let's just say increase the amount of water slightly. Oh, we've flooded most of the planet. That's a little extreme, but you can do this if you like. Anyway, let's move on and look at some actual orbital mechanics. Okay, so this is what's called a braid formation. It's 3 stars very carefully placed in a figure 8. Now, what's interesting about this is that it is actually stable. If you give one of these a bump, they will more or less self-stabilize, and accounting for the errors in integration system, it is stable. But it only works if they all have the same mass. So if I pause this, you see that as 0.452, 0.452, 0.452. So let's take one of these and change its mass just a little, right? So select this and let's make it 0.475. So we're changing it by 1/4% roughly. And then let's see what happens. Hopefully, oh, there you see already, just by a tiny change in the mass, things are starting to fall apart, and they will fall more and more apart. You can't make it stable unless all 3 objects have the same mass, and that is incredibly unlikely in the real universe, right? You can come up with all sorts of stable configurations, but it's highly unlikely that you would have 3 things of the same mass, and you can see it's just getting worse and worse. I can't even tell you which one was the original one that I tweaked, but these things will probably eventually pick up some very eccentric motions and maybe stop. Let's see if the figure 8 stops, right? The figure 8 is where they pass between each other, and while the deviations are getting larger and larger, it does seem to be stable-ish. It's not stable, but it does seem to be still repeating the figure 8. But eventually what'll happen is one or the other will fall out of this sequence. Whoa, there we go. Starting to get some really big deviations here. And 2 of them collided and shot off. That perhaps isn't realistic, because there should be... I think the integrator perhaps broke a little there. Okay, so this is an example of a composite body. Okay, this is kind of a hack. What I've done is I put 2 Earths here and basically forced them to stay still. Now, because they don't have a spherical gravity potential, the orbits are not perfect ellipses, right? So in this case, the argument of the perihelion is precessing over time. So the whole orbit in its eccentric orbit is moving around like that. And this is... Now, this is obviously a really extreme version. In reality, most objects do not have perfectly spherical gravity potentials. The Earth, for example, has an equatorial bulge, which means that orbits get twisted around by this bulge, and in particular, you can use this equatorial bulge to do things like create solar synchronous orbits. Now, in the game, in the sim, it's really just a hack to hold these 2 things in position and then add a 3rd object. In fact, it's very hard to put the 3rd object into the exact location. Another example where non-spherical gravity sources is really important is, of course, Rosetta, which is orbiting a dumbbell-shaped comet right now. And they have to be very careful when they... pick their orbits to make sure they don't get perturbed too much and end up crashing into the comet eventually. Okay, so this is one of their experimental database simulations. This is not about orbital mechanics. This is taking data on the stars near the sun, and you can see them all in space, roughly represented by their position and color. And of course you can zoom all the way in. I'm just zooming in with the mouse wheel. You can hear it clicking. There's a lot of zooming you have to do to get in close to the sun because space is big. But this is all about looking at the chart mode, where I can select them and put them, for example, in order of increasing mass. This is really interesting because, of course, at one end you have gas giants, right? The low end you've got gas giants, and as we get more and more massive, you end up with red stars, and as you get more massive still, they become yellow. We get something like our sun is, I don't know, it's here. There's our sun. And as we get heavier still, we get less yellow and move towards white and ultimately blue stars. So a really interesting thing to plot is what's called the HR diagram, the Hertzsprung-Russell diagram. And I'm just going to customize these scales just a bit here. What this is, let's change surface luminosity logarithmic, okay, and luminosity, let's invert. Oh, we don't want to invert that. We want to invert that. There, that looks a little better. Okay, so this is essentially a two-dimensional graph that we've got here. I'm going to pick this one as the center so you can actually see. So mostly we're interested in this section here. What we have is going towards the right is increasing temperature, and going upwards is increasing luminosity. So the main group here is kind of like a line, and actually there's two lines because they haven't got their data imported correctly by the looks of things. But if I make this make this a logarithmic chart, it becomes much more obvious where everything is. So yeah, you have this kind of line of the main sequence. And again, you'll notice we have red stars over in this direction and blue stars in this direction. These are again imported ones which have bad data. These ones clearly have luminosity of 1, which is a placeholder value that makes absolutely no sense at all. But these outliers here, these are legitimate. I went in and manually corrected them. These are all white dwarfs. So at the high end you have Sirius B, which is stupendously hot. It's 25,000 degrees centigrade, but its luminosity is very low, less than 2.5% of the luminosity of the sun. And you have to remember, Sirius B sits next to a star which has a luminosity 10 times that of the sun, so it was very hard to see. It is a white dwarf. It's very small, very, very hot. It's the remnant of a star which expanded to a red giant and then puffed off its outer layers and collapsed back to an inert core which is super hot but is cooling down over time. Similarly, we have WD 1142, which is an older one, therefore it is cooler, and then we have Van Manen's star, which is a quarter of a solar mass. It's 3 billion years old and its temperature has dropped to 6,000 degrees centigrade. So what happens is the stars, they heat up and then they kind of drop down here, right, over time. This is like an evolutionary chart almost. The stars move around in this. As they evolve, they drop down, become a white dwarf, and then they cool off in this direction. They basically get cooler and cooler and fainter and fainter. And that's Hertzsprung-Russell diagram. It's pretty complicated, but it's, you can find all sorts of interesting things. Oh, actually, I can add an extra axis to this. One thing I could do is add mass, which will be telling. Now, obviously from this angle it all looks good, but as I turn it around, ooh, look! Anyone notice another link there? As we go to brighter and brighter stars in the main sequence, and hotter stars, the mass increases. This is a standard relationship that you will see with stars. The fainter the star is, the lighter it tends to be. The redder, the lower the star mass is, the more red it tends to be because it's cooler. Of course, there's an exception to this. When I played Solar, people were like, why are you mad that the low mass stars are blue? Surely red giants are the biggest stars. And red giants are the biggest stars. Let me just put a red giant on here. I think it's possible. I can add, I'm going to look for one. Now, Betelgeuse would be interesting, but unfortunately, if that's the size of Sirius, Betelgeuse will be like bigger than the graph itself. Aldebaran, though, I think we can add that in, and let's just try it. and it just drops in there. Okay, brilliant. Okay, it's kind of hard to see, but you can see where it sits on this chart, right? It is cooler, so it's more towards the left side of the chart, but it is also bright, so it sits up here. It is, it's a 1.7 solar mass star, and it's a 2 billion year old, and so therefore it has evolved into this bright, hot star that it's not as hot as, say, an equivalent 1.79 solar mass star. So you see, this star is younger, it is not evolved, it's hotter, but because this one has a larger surface area, even though that surface area is cooler, it is brighter overall. It's quite a complicated thing, stellar evolution. Now, sure, these tools will evolve, but right now, obviously the data is a little buggy. Let's move on and take a look at some other things. Okay, so one of the more popular features is collisions. So I'm going to crash Eris into the Earth, and we can watch this happen. Look at that. So the collision generates tons of fragments, which of course fly off in their own orbits and proceed to zip around the Earth. Now notice that the oceans are boiling. That's because, of course, they're modelling the climate here, and the temperature is up around 900. Having a planet or moon smash into you generally doesn't do great things for your habitability. It's kind of cool to watch this. You can run this at higher speed. They have a whole menu just for generating collisions. You can, of course, do Earth versus Moon. Bang! There it goes, and it's even bigger still. I bet you the Earth gets even hotter. Climate 4,000 degrees. Yes, it's turning into a sun, basically. That's not good, having these kind of things smashed together. But if you go into main or open, there's actually tons of different options here. That's the plan. We can have galaxy colliding. Yes, galaxies colliding. Just watch this go on here. So this is simulated in a slightly different manner, but it's all same laws of motion and everything. You're not simulating every single star in these galaxies. There would be too many to store, but they are simulating dust clouds and clusters of stars. So as we watch them come together, you can see this thing getting pulled up in towards the core. The core is, of course, where most of the mass of the galaxy actually is. Now, I think one thing that's missing from this is that gas clouds don't collide, because what happens when galaxies collide is the gas clouds kind of bump off each other and form bigger gas clouds, but the stars, they just kind of fly past each other. And in this case, it looks just like the stars flying past each other, possibly because that's easier to code. Anyway, that was a fantastic finale to Universe Sandbox 2. We will be looking at it more in future, but until then, I'm Scott Manley. Fly safe.